Hello, and welcome to our talk on Intent Driven Orchestration. If you're interested in understanding how a new approach to defining service level objectives can be used to support use cases such as dynamic right sizing your applications, the avoidance of under or over allocation of resources, perhaps the promotion of greater manifest portability between environments, and particularly with the related goal of having semantic app portability, then we think you're in the right place. I'm Adrian Hoban, an architecture lead for cloud native resource orchestration in the Network and Edge group in Intel. And I'm joined today with Thijs Metsch, a senior researcher in Intel Labs. And together with other technologists in Intel, we've created a new framework that targets these types of use cases. Now, I want to say from the get-go that we do not consider IDO to be a service assurance offering, but we do think that it can contribute to service assurance, particularly in relation to items such as service degradations tied to suboptimal resource allocations. And so I'd like to take a look first at the current state. So if we look at Kubernetes today as our starting point, primarily due to its ubiquity as a mechanism for deploying cloud native workloads, there are three implicit quality of service models in Kubernetes. One is the best effort model, and for this, the user does not need to specify any CPU or memory requests. And instead, you leave it up to the worker node OS scheduler to take care of that resource balancing. There's a burstable model, and with burstable, the user can specify a range of resources. The guaranteed model is where a user is more precise, and they say explicitly what they need from the environment. And in addition to these types of QoS models, there is an ability to add specific requests for features in the environments. And what we see is that workloads that require really exact deployments that have perhaps deterministic high performance needs or really low latency type requirements, they depend quite a bit on this idea of guaranteed QoS models. And you know, it works really well for many use cases. It has syntactic portability between environments, and it's really easy to consume. But one of the things it doesn't have is the ability to confirm on the user the exact nature of the resources that you get allocated. So if we take the example on screen here and we look at, let's say, the CPU allocation and 2 cores as an example. But really what this means in Kubernetes is that it's 2 units of compute, and they're defined based on the underpinnings. So is it 2 physical cores, 2 virtual cores, 2 threads from a hyper-threaded sibling cores, from a processor multiple generations old, or from our latest and greatest high-end server models. And if you combine that with things that the cluster admin may have done, such as deciding or not to deploy static policies for Kubernetes, it really does lead you to a place where your compute-related ask is something that is really dynamic between different environments. Now, there are mechanisms for determining what right-size resource request is. You really need to have a knowledge of your application. Ideally, you have a really good knowledge of the environment in which you're deploying in. And sometimes you maybe even need a knowledge of the other workloads in the environment. But in a long-lived cluster, that right starting point, can you be really sure that that's the right resource allocation you need to carry into that cluster days, weeks, or months ahead, particularly as other things may change in the cluster? So with that perspective, I'd like to introduce you to intent-driven orchestration. And this is a new capability that we've developed that can be plugged into the Kubernetes control plane. It brings with it a new API, and this new API promotes the definition of workload objectives as in key performance indicators. And it does this in lieu of expecting that the user understands or can request what the right resource requests need to be for that particular workload. Now, each objective, as we've defined it, is effectively unitless from an IDO perspective. The important point for IDO is that we can associate that objective with the means to monitor it. Now, the example shown on the screen is a 30 milliseconds latency target. It comes from one of our default queries that we've created, and it's based on a P95 profile. Now, this is coming off a service mesh in this deployment, but the interface itself is not limited to this. It's designed to allow application developers to specify KPIs that they care about. So if that KPI happens to be an images processed per second, or an images latency per second, or latency type of a target, or some variant of application throughputs, completions per second, requests per second, it doesn't really matter, provided they also give IDO the query configuration so IDO can continuously monitor that objective. Now, we are looking at multiple types of objectives initially. We have latency, throughput, availability, and power and scope, and others under consideration. IDO itself is a closed loop system. It takes these inputs, and through a set of sophisticated planning and actuation components, we can dynamically determine what that right resource ask is for any point in time in the cluster. It then updates the application manifest, things that we provide to Kubernetes to figure out what it has to actually deploy, and triggers Kubernetes to leverage its advanced scheduling and resource allocation mechanisms, really to take over and deploy the workload from there. And so with that intro, I'd like to introduce Thijs, who's going to talk us through that planning capability in more detail and demonstrate IDO in action.
Yeah, so let's talk a little bit more about planning. And if you just think about the process of planning, what it actually means, it's kind of like figuring out what step of actions do I need to take to get to a desired goal. So if you look at the example here on the left, so let's assume you have a set of random blocks that are randomly positioned. If you give that to a planning algorithm, with the planning algorithm, I can actually figure out from what's the right set of moves I need to make to the block so that I get that neat stack A, B, C. Now, we're obviously not dealing with blocks. We're dealing with the objectives associated with an application which is deployed somewhere. What we're trying to do is kind of like figure out which kind of orchestration activities do we need to take to move the objectives in the right direction. Planning basically therefore allows us to translate service level objectives that we showed earlier into something more actionable, which actually means that, for example, we can do the right resource allocations under the hood. We believe that planning is actually quite essential for achieving autonomic systems in the end of the day. Specifically, if you think about properties of self-tuning and self-healing, just imagine that you can observe your service level objectives over the lifetime of your application. And let's say the planning component can automatically make adjustments to resource allocations as time goes by, make sure that we always hit our targets and goals. Planning in itself is not necessarily new. Planning has been around and has been used in many kind of use cases. But we still feel this is kind of like a new, novel case to embed it into a control plane like Kubernetes. Let's say, in contrast to scheduling, where we look at, okay, when and where do we place workloads? For planning, we really try to figure out what and how do we need to set up the system to meet the objectives that the user has defined. What we'll now do is actually take a quick look and see this thing in action. What you're seeing here on the left-hand side is a Grafana dashboard. It shows the latency and throughput of a function which is being deployed on a Kubernetes cluster. On the right-hand side, you see a dashboard of the planning component. So we can actually track the actions that the planning component recommends as we go along. Currently, initially, we have set a P95 objective for this function. We want that to be less than 30 milliseconds. Initially, the system is not able to reach that. So one of the first actions that the planning component actually does is actually do a CPU right sizing. In this case, it suggests that 1600 CPU units should be allocated to this function for it to operate within the bounds of what is defined. So this basically roughly means that 1.5 CPU cores are associated with the workload. This information is now added to the Kubernetes pod spec and is basically enforced to the normal Kubernetes mechanisms throughout the system. Now, this is obviously not the only action that the planner can take. Given the context of what's going on, the planner can take different kinds of actions. So what's going to happen now in the background is we're going to increase the load on the function, which will actually lead to a little spike in latency. And at this point in time, the planner actually takes the decision to scale it out. So we're now actually running 2 instances of the function at the same time. And you will eventually notice that we get our P95 service level objective back under control. The one thing I want to emphasize here is really that the only way that the user interacts with the system is through the objectives. He or she does not need to configure any autoscalers or needs to go into the details of setting CPU resource allocations correctly. This is all done automatically through the planning component. Basically, the user is steering the system purely through the objectives. Just to demonstrate that point, what we're going to be doing now is we're actually going to change the P95 latency objective. So we're going to change it from 30 milliseconds to 50 milliseconds. And one of the first actions you're going to notice that the planner actually takes, it actually frees up some resources. So in this case, it now thinks that a little bit less than 1.5 cores associated with the workload or the application is enough in this case. Note obviously that these numbers can heavily depend on the context that you're in. A different CPU revision or a different platform that you're running on will lead to different numbers being set here. Just to complete the demo at the end here, we can also showcase, for example, that if a load goes away, that actually the planner will scale in the application again, and we're just running a single instance of the function again. So this kind of like was a quick first introduction to the intent-driven orchestration framework, where we kind of like really want to showcase that the user can define what he or she really cares about, which are the objectives, and we'll add an orchestration stack like Kubernetes take care of the rest. It's really a fundamental shift in how we do orchestration. It really allows that ease of use for the user, and it obviously also enables some benefits for the resource or the cluster admin. For the cluster admin, it's a benefit to better understanding what the intents and the objectives from the users are. So therefore, I can basically tune my platform for more efficiency. If you want to try this out, you can go to our GitHub page and you can actually try out the Intent-Driven Orchestration Planner for Kubernetes that we've open sourced over there. So this is quite a new way. This is still early days for this technology demonstrator, but we're quite keen to see how this can reshape how we do orchestration in the future. With that, I want to say thank you for watching this video. If you have any comments or feedback, feel free to get in touch with us.